Okay, so let's get started. So what I wanted to do today, we're gonna we're gonna enter somewhat of a new part of the class, a little bit of a topic. So what I'll be talking about today is what are called semi-direct products. So it's a different kind of example of groups than what you often hear about. And one reason I kind of wanted to there's several reasons I wanted to talk about this topic in this class. It's not actually, so this is something which you're going to have trouble, I think, finding if you look somewhere else, if you're looking in other books to try to find out more about this. This is I think this is actually kind of a central topic for reasons that I'll kind of explain. It does a lot of explaining what's going on in both in non-relativistic quantum mechanics, the kind that we're talking about, but also in what we'll talk about more in the second semester in relativistic quantum mechanics. This kind of same idea is even more central. So anyway, so that's what I want to talk about today. Maybe before I get started, let me just kind of quickly summarize what I was doing before, where we are before, what the kind of overall picture I've been trying to give you so far is, and then we're going to then I'll go to this new material about the Euclidean group and about representations of this different kind of group, these Euclidean groups. Okay, so let's see. So what we're doing so far, what the story I was trying to tell you was really about that it's kind of a point of view on what quantization is. And so the idea is that it's really an interpretation of what Dirac originally wrote down, Dirac's idea of what a quantization should be. Is that it's really it really is just find a unitary representation of the Lie algebra. This is the goal. This, in some sense, is what Dirac originally kind of wrote down as kind of a goal when he saw what Heisenberg had been doing. Lie algebra, and the Lie algebra is just functions on M, where M is phase space with the Poisson bracket is Lie bracket. Okay. So this is an infinitesimal Lie algebra, and what you'd like to do is, I spent a bunch of time talking about Hamiltonian mechanics from the point of view of exploiting as much as possible the fact that the functions on a phase space are formally algebra in the Poisson bracket. But from this point of view, what quantum mechanics is saying is really just that if you believe classical mechanics is all about this Lie algebra, well then, and you know that representations are interesting, well, quantum mechanics is really nothing more than saying, we should look for a unitary representation of this Lie algebra. And then if you do this, what you find, you find that you can't actually quite do this. That it actually, let's just sticking to polynomial functions. If you take functions that are quadratic, no more than order 2, then you can actually get on the nose a unitary representation. But if you try and extend it to higher order functions, to cubic or higher order, you get this no-go theorem, which says that you can't you can only get a representation up to these ordering ambiguities, which kind of ruin your ability to get a true representation. But what you get is you find out is you can do this. This works for the subalgebra. Of quadratic functions. So these are the things with the basis 1, Qj, Pj, Qj, Qk, Pj, Qk, and Qj. So if you form all such things, what you find is that there's this thing, and there's two subalgebras. There's this guy. This guy is the Lie algebra of the Heisenberg group. And this guy is the algebra of the symplectic group. And then what you find is that the what you find is that our the canonical quantization where you take where you take H is functions on RD on just D dimensions, half of this. Let's say RD, D, and what you do is you make QJ. You take under the representation, this basis element of the algebra becomes minus I QJ. That operator PJ goes to minus I PJ, and then you deal with the quadratic things by just multiplying these guys. But then there's one case where you have to worry about which order you do it, and that one you do by QJ PJ goes to minus I to half. Sorry, for when these are the same, PJ plus PJ QJ. So since the P's all commute with each other and the Q's all commute with each other, mostly it doesn't matter which order you do things, except in this one case, then you have to be careful that you get the order correctly. And what you find is that so you find that you've solved Dirac's problem, and you've got this kind of nice array of operators, one for every kind of every quadratic polynomial on the phase space. And the Stone-von Neumann theorem then tells you that even better that this is really the only solution to the problem, that there's really only up to kind of a unitary transformation of basis, like for instance going from Q's to P's in your function space by Fourier transformation. That what you've got is this is the only such representation. It's a nice irreducible representation. There's also one subtlety which we'll talk about a little bit more later. That this is this gives you a representation of the algebra. If you try and exponentiate it and turn it into a representation of the Lie group, everything's fine here, but here you end up with a double cover, just like when you had spin. Okay, so that's the story that I'm really I'm trying to tell, and maybe the part of it that we're going to get to today, maybe just a few other comments about it. One is that this kind of generalizes what the standard story that you'll often hear about symmetries. So the usual, let me just say this, is that the usual symmetries is is that you're looking for things that Poisson commute with H, and that later on are going to commute with the Hamiltonian. Okay, so the usual story about symmetries, and that you'll hear in most discussions of quantum mechanics, is that a symmetry is going to be generated by some kind of function on phase space, which commutes with a Hamiltonian. And then if something commutes with a Hamiltonian, then when you quantize, you're going to get an observable operator is going to commute with a Hamiltonian. It's going to be if you know the value of that, if you know the eigenvalue of that operator at a given time, it's going to continue to be the same eigenvalue for all later times. Or here in classical mechanics, if you know the value of this function at a given point in phase space, as you move along in phase space, you're gonna keep the same value. So there's some kind of amongst all of these functions we've got, some of them are going to commute. Nothing that I've said here says anything at all about the Hamiltonian. So this is all completely independent of what your dynamics is, what the Hamiltonian is. But once you pick a Hamiltonian, some subset of these things is going to commute with a Hamiltonian and going to give you your usual kinds of symmetries. But you're also going to get other kinds of operators which which come along as part of this package, which have really interesting computational relations with each other, and which actually generate very nicely this the action of this group. But they don't necessarily commute with the Hamiltonian, and they don't necessarily give conserved quantities. So a simple example would be just if you have a standard Hamiltonian for a free particle, your p's are going to commute. P squared is going to commute with it, but Q squared is not going to commute with it, and your Q's are not going to commute with it. So, this Q operator and these Q squared operators are certainly interesting things, but they don't generate symmetries in this sense, but they actually kind of generate a nice story, which you can think of as a story about symmetries in this larger sense. So that's the story I wanted to tell you about before. But let me just say, then to kind of lead into where this is going to go from Go today. So let me just get rid of this. Okay, so okay, so now, if you exponentiate these guys, as I said, what you get is the exponential of these guys gives you the Heisenberg group. And the the exponential of these oh, sorry, this is wrong picture. This should be here, and this should be here. Sorry about that. Okay, so so then the exponential of these guys gives you the symplectic group. Again, there's a little bit of a problem that because of the ordering, because of the way these things operate, you actually are going to get a double, not quite this group, but a double cover of it, just like the spin double cover. But I won't. That's not too relevant for what I want to say right now. But the thing which you have to watch out for here, which is funny that's going on here, is that you have a subalgebra of these guys, and they exponentially give a subgroup. Then you have a subalgebra of these guys, which exponentiates to give this group. So you appear to just have kind of two independent groups acting on your representation. But there's something funny going on here, is that you have but okay, and maybe and so this is what I'm going to explain today, is that you don't just get the product of this group and this group, you get something called a semi-direct product. And the reason it's a semi-direct product is that these things are interacting in a non-trivial way. Is that you also have kind of quadratic linear is equal to linear. So the problem is that they're non-zero plus home brackets between these guys and these two guys. This guy commutes with everything. Plus one commutes with everything here, but these two guys have non-trivial commutation relations with these guys. So what's happening is that this group here is acting in a non-trivial way on this group here. This is the phenomenon that I want to kind of go and give you some general theory for. And so what's happening, you'll see, is that this group is acting as kind of automorphisms of this group. It's moving everything around in here while preserving the group law. But this is a kind of Well, I'll say more about it, but this is actually a fairly difficult kind of example of this phenomenon, because this is a non-commutative group. This is a non-commutative group. You've got one non-commutative group, moving around and acting in a complicated way by automorphisms on another non-commutative group. This is kind of one of the harder problems in mathematics to think about. But the easier thing to think about is to realize that within the Heisenberg group, if you just look at the PJs, which generate translations, and then just look at the combinations of look at the combinations of Q and P, which generate rotations, and so you end up with a subgroup here, which is SO. You can do this in any dimension, but mostly you think about it in 2 dimensions. But you have a group here of this is generated by rotations either in the Q's or in the simultaneous rotations in the Q's and rotations in the same rotation in the P's. And this here is RD, and it's the same. It's also, and it's just translations in Q. Translations in Q, and then but then you have the same kind of phenomenon that the rotations act on the translations, and you have the same kind of symbol here saying that you have a bigger group here, but when you put these together, they interact in a non-trivial way, and this actually has a name which I'll call E of D, which is the Euclidean group. Okay. So this is what I want to start talking about today. What I want to do is kind of start talking about these Euclidean groups as a kind of a new example where there's going to be new phenomena for how to quantize them. And in some sense, we're going to quantize them what we're going to do is we're going to take advantage of the fact that this is just a subgroup of a group that we've already quantized. So we already have a nice representation. We already have a nice, very, very interesting representation of this guy. So if we just restrict it to the Euclidean group, we're also going to have turns out we're going to get the interesting representation of the Euclidean group. So that's the plan. Okay.
But is reflection of a member in Euclidean group?
Okay, so I'm actually not taught. Yeah, so I'm mostly not going to be thinking about the reflection. I'm just going to stick to the component of the identity. So with the S here. I mean, you can also ask about how the reflection acts, and you can also ask about O. But yeah. Anyway, I mean, and the way that I'm thinking about everything, I'm kind of building it up by thinking about what's happening at the Lie algebra, and that's telling you what happens near the identity. So you have to do something extra to think about what happens if you go to the other component and do like a parity transformation. Okay. So I'm not going to do that right now. Okay. Any other questions about this? Okay. So this is where we go. Okay. So what I'm going to do is So mostly I'm going to start by talking about what happens in well, you can start by thinking about what happens in 3 dimensions, but really the story is that two dimensions is fairly special because in 2 dimensions there's just kind of one rotation. There's a rotation about one axis, and it's a commutative group. The minute you go to SO3, it's a non-commutative group, and so most of the general theory and the complexity of what's going to happen already starts to appear for 3 dimensions. So it's often might as well just kind of think about 3 dimensions, and then it's fairly easy to see what's going to happen in higher dimensions. But let's start with this. So instead of doing what I was doing before, which was kind of starting out with these relations at the level of Lie algebra and then kind of exponentiating and getting and trying to find the group, which is what I did for the symplectic story. Here, you know, the group is actually something very, very concrete. It's the group. It's, you know, the name Euclid goes back all the way to the Greeks. It really is just the kind of obvious group you have right in front of you of kind of, I can translate things back and forth, or I can rotate them around, and the kind of structure of space that's right before my eyes kind of indicates that that's not going to really change. That's often not going to really change what's going on if I rotate things or move them around. So this is the Euclidean group. That's what we're going to talk about. And so maybe it's so a good way to think of this is that you think of it as pairs. Anyway, let me just talk about it for E is equal to 3. So elements are pairs A vector and R, and this is so this is an element of R3. This is an element of SO3. Again, I'm not going to worry about the other component right here. Okay. So what we now, if we just had the product group, if we just had you know, R3 cross SO3, then, you know, nothing interesting would happen when the group law would be just, you know, use the additive group law on these guys and multiply these guys together. But something more interesting is happening, that, you know, if you think about these group elements as doing a transformation, well, something interesting happens if you do 2 transformations in a row. You don't just add these and multiply these. Something more interesting happens. So the way to realize is that, you know, this acts. You look at the action of these guys, V3, on vectors. So this acts. So a pair acts on R3 by so V by V vector goes to so R. Let's make it. Let me write it. Write it in this way. I was writing it. Well, R. Let's write it this way. I guess it's going to be R. It's going to you rotate the V vector, and then you add you add A vector. Okay, so this is the action, is that you rotate, and then you translate by A. So this is the translation. This is the rotation. Now the problem is, if you do 2 of these, what you find is that so A1. So this is a calculation. I'll do this quickly. This calculation's in the notes. If you do A1 R1, and then you act on A2 vector R2. So if you act first by this on here and by this on there, and do a short calculation, you find that what you get is well, this just translates by a 1 vector, and the rotation is the rotation is what you'd expect. It's first this guy, then you do this guy, so it looks like R1, R2, V vector. But something funny happens. Here you have an A2. Here you're translating V vector by A2, but then this guy is getting rotated by this. So you have something. You have this R1, A2. So what happens is that the vector gets rotated by the product of these 2 guys, as you expect, and there's this translation is the one you expect, but there's one of the translation is not by A1 plus A2, which it would be in the product if you use the product group. It's by A1 plus R1 A2, and this is where this action of the rotations on the translations. This is where the fact that there's a non-trivial axial rotation in translations comes out right here. And so then you can rewrite this kind of just in terms of what happens when you multiply pairs by A1 R1 multiplied by A2 R2 is equal to what? Is A1 plus R2 A2. So this is our group law. So we're putting a group law on these pairs, which if this R2 was just the identity, then it would be just the product group law. But it's actually something more interesting is going on, and this is what's called, makes it a so-called semi-direct product.
Should that be R1A2? In the last
Yeah,
one?
thanks. Thank you. Yes, this guy's, I think. Thanks. Okay, and so this. I mean, I won't write it down, but this is, actually, if you realize that what I wrote down here actually doesn't depend upon the fact we're in 3 dimensions. It's the same formula in D dimensions, and this is just this is just the this formula is just the definition of the Euclidean group, which is R. And I'll say more about the notation in a minute, but we write it this guy. So it's pairs of, now if you think of these as pairs of translations in any dimension with rotations in any dimension, then and you multiply pairs like this and use the fact that rotations act on translations, you get the general the Euclidean group in any dimension. Okay, now so I mean this for most calculations this is a you can just work with the definition in terms of pairs, but I guess I should have said that you could also, so instead of so it's a so another sometimes useful fact is that this is a matrix group. So you can instead of working with pairs and the multiplication law that I just erased there, you can instead take so you take E of D is a subgroup of the invertible D1 D plus 1 by D plus 1 matrices, where so elements. So you put R here, and you put A vector here, and then you put a 1 here, and a zero vector, if you like, here. So this is D dimensions, and then this is just a one-dimensional piece. So this is a D plus 1 dimensional by D plus 1 dimensional matrix, and it's the matrix which has a D by D orthogonal. So this is a orthogonal D by D matrix. D by D matrix. And then here you just have lined up along here you have the components of the translation, and over here you have 0. And if you work out that if you multiplication law, so multiplication of these, so matrix multiplication gives our group law. So you can see if you multiply 2 matrices like this, what's going to happen is the 1's are going to stay put, the 0 is going to stay put, you're going to multiply the two r's here, and here you're going to get you know, the first translation plus the, you know, anyway, and you get one translation plus r times the other translation, plus one of the r's times the other translation. So another way of getting at that that group law is to say I really like matrices. I'm going to stick to matrices. So it's not anyway. Actually, working with this group in terms of matrices of this kind isn't, I don't know. Sometimes it's useful for getting unconfused if you really want to, if you're finding what the way the group law is a bit too abstract about what it's doing. If you want to say, okay, I really want to go back and think about the group law in terms of matrix multiplication, then it's a good idea to do this. Okay, so that's the group law, and then now let me okay, so let's do a general. So this is a specific example of a general thing, and this is what's called it. So this is what's called a semi-direct product group. And so the definition is going to be that. So what you're given is you're given a group given, let me just say it. A group K, to a group N. So this is going to be the analog of the rotation group. This is going to be the analog of the generalization of the translation group. And 3, an action of N, I'll call it phi, of K on N by automorphism. And what this means is that okay, so phi just means that for every element, so for every element of K, you have a phi K that takes N to N. It acts on, takes N to N, and it preserves the group law that N1. Anyway, phi of N1 times N2 is phi of N1 times phi of N2. I guess I should write it out. So phi of N1, N2 is phi of N1. Okay. So this is the general data, but you should think of this as just we're trying to kind of come up with a very general context to talk about the putting together groups of rotations and translations, where the rotations act on the translations by a known map. So if you're given all of this, maybe let me then write up, finish this definition up here. The semi-direct product group, and I'll write it N, very simple, K is the set of pairs so NK. So we take an element of N, an element of K. Okay. Again. So you look at the set theoretic product of these. Just take one of these and one of these, and make pairs. And then what you want to do, and then the with the group law. What is it? It's that N1 K1. If you multiply it by N2 K2, well, what's going to happen? You're going to have N1. Okay. So the K's are just going to do what you expect. You're just going to get a K1, K2. Okay. But something funny is going to the group law of the ends is going to pick up a contribution from this phenomenon. And if you write the group law in this multiplicative form as opposed to the additive form that we're using for the Euclidean group, then you would write it this way: is that this is what you're doing is you're acting by this automorphism. Okay, and I guess what I did is okay. Sorry. So I should probably a better way to do this is to put a k as a subscript here. I should have put it here. It's all right. Yeah. So for each k, you get a map phi k, which acts on n, and so you're going to have a phi k k1 acting on n2. And then you're going to multiply that. You're going to apply the n group law with n1. So if this were 1, it would just be the product group law, but it's this automorphism that goes in there that makes something interesting happen. Okay, and then so in the notes, I actually kind of work out what happens with the you can check, to show that this is a group. You have to. It's a little bit of work to show that you have to use this fact to show that it's actually a nice associative group law, and that you can actually write down every element here has an inverse, and you can write it down. I guess whatever. Okay, and now so maybe just something to say. I guess I could. Maybe something about notation. So there's kind of two facts about this notation. So the first and maybe most important fact is that it's actually not a good notation because it doesn't tell you something important. But so it's problematic. Because it doesn't mention phi. So better would be, and sometimes would be n k, and better would be to kind of put. So a better notation, what you'll sometimes see is that people will actually write the phi underneath the so-called semi-direct product symbol. And so, because the point is that you actually don't, well, normally you don't actually need to do this because it's pretty clear what phi is going to be. So for instance, in the case of the Euclidean group, there's really, it's pretty clear that you want to use you have rotations and translations. The action you want to use is to rotate the translations. Here, if you're doing this abstractly, you have to, the definition does depend upon which phi you choose, and in many cases there might be a bunch of different phis. And if you take phi as the identity, then you just get back the normal product. So it's a little bit of a, anyway, it's one thing to watch out for is that this is not telling you something when you write it down. And this is for, if you've studied some abstract algebra, you find what I'm saying now will make sense. If not, you probably don't really worry about it. But it's just that the reason for this weird symbol is that n N is a norm. So N is what's called is a normal subgroup. And that's and the symbol for normal subgroup is that instead of using the subset symbol, you often use this symbol. Anyway, so if you studied some abstract algebra, you may have, and you studied that. And what you learn at some point is that if you have two groups, and and one of them acts on the other, you can put them. You can if you have two groups and well, if you have a subgroup of a group, it may or may not be what's called normal. And one way of saying that it's normal is that if you take the quotient of the full group modulo the subgroup, you actually get another group. In general, if you take a quotient of two groups, you just get a set. You don't get a group. But if you actually do get a group, then it's called a normal subgroup. And in this case, it's anyway. So what the way a semi-direct product works, the N is always a normal subgroup of the whole semi-direct product group, and the quotient of it by N is just K. So anyway, so this is kind of a comment if you've seen normal subgroups in an abstract algebra class, and it's a comment also about why why this symbol in that context explains this symbol here. Okay. Okay, so that's the that's the general story, and we've seen we've seen two examples. We've seen E of D, and that's R D semi-direct product SOD D. But and we've seen a more sophisticated example, which was the Heisenberg group semi-direct product with the symplectic group. And again, and here the notation isn't telling you about what the automorphism is, but the automorphism here is just kind of the symplectic transformations. If they act on the Q's and P's, they preserve the Poisson bracket, and so they preserve this group, and that's the automorphism in this case. So this is a much more sophisticated example than this, because this group's quite a bit trickier than this group, and this group is much trickier than this group. But the interesting, anyway, this is kind of the thing that underlies quantum mechanics, and this is the Euclidean group. And there's actually a name for this thing. So this thing is often called. Sometimes, well, people do give this various names. One name that you'll see for it, if you want to look in the literature for this, you'll find it. It's the Jacobi group. Okay, and so that's this guy. But he's actually not so this is actually a really important group that kind of has all sorts of applications, and you see everywhere, and it's kind of crucial. This is a more exotic thing you don't see very often. As I said, this guy you could turn into a matrix group if you wanted to. It's not hard, and showed you how to do it. This guy, in principle, you can also turn him into a matrix group if you want. You can kind of write matrices, which where you put together a symplectic matrix and an element of the Heisenberg group. But the problem is that this matrix construction becomes kind of more complicated. You end up with these large matrices doing kind of confusing things, and it's not so helpful. Okay, So what we want to do, so this is the abstract story, and this is actually the main cases, the two main cases we care about. We're not actually going to, as usual in this course, I'm not going to kind of go very much into general theory, and I'm just going to stick to these kind of central examples. Okay, and actually, maybe though before. Yeah. Okay. Actually, maybe let me add one more example here. And there's the Poincaré group, and that's this is what you get. So the three-dimensional cases is what you get in 3 dimensions, of three-dimensional rotations and translations. If you try and do special relativity and think about space-time, so that now you've got a 4-dimensional space-time with 3 space dimensions and 1 time dimension, then what happens is you end up having a similar thing, but instead of rotations in the usual rotations in 4 dimensions, you have rotations in 4 dimensions that preserve not the usual inner product, but an inner product where you have 3 positive coefficients and 1 negative coefficient. So that's SO31. Well, this is called the Lorentz. This is called the Lorentz group. And then this guy here, again, you're looking at 4-dimensional translations, but this guy's going to act on these translations by it's going to treat one direction differently as the time direction. So you can write this as R31. So, I mean, this is a fairly complete list of the actual cases where you're actually going to care about in physics of this. It's going to either the rotate the Euclidean group in any dimension, especially in 3 dimensions, or the kind of generalization to this case of an indefinite 3-1 metric where you get to do space-time and special relativity, and that these guys, and you're often going to treat these groups by embedding them inside a standard kind of canonical quantization story, which is a story about how this more sophisticated group acts on everything. Okay, so that's that. Now, I guess then the next thing I wanted to do is then say something about what happens in the Lie algebra. Okay, so now I've started at the group level, and I want to ask what's the Lie algebra? What do tangents to these things at the identity look like? And how do you so how do you if you have an abstract thing like this, how do you think about its Lie algebra? And how do you think, because again, its Lie algebra is going to be kind of a Lie algebra based on pairs of the Lie algebra of something Lie algebra of n and something Lie algebra of k. But again, you're going to use somehow this automorphism phi is going to make an appearance. Let's do that. Okay, so let's do. It says, so this is an example. Since we defined Lie algebras in terms of matrices, in terms of the things you exponentiate to get group elements, this actually is not a bad idea to think about these groups in terms of the let's go Lie algebras. So let's do this. Let's work out what happens for E of D. SOD. Okay, and so remember that these were matrices. The elements are matrices. R A vector 1, 0 vector. Think of things like this. Now, if you want to, so you want to ask what are the matrices that you're going to exponentiate? So there should also be we want to write our Lie algebra elements as matrices. So there also should be a set of matrices which, if you exponentiate them, will give you these guys. And so what you do is you write this. So the correspondence to the Lie algebra elements are things that you exponentiate to get those are matrices of the form. Okay. Well, here it's just x. Here you just put x, where x is an element of the Lie algebra at SOD. And so, as far as this d by d square is concerned, when you exponentiate, you're just going to exponentiate these guys and get these guys. It's the standard SOD story. And then the thing, that when the thing that you're going to exponentiate to get 1 is you just have 0 here. And again, you have a 0 here, and it turns out there's an a vector here. So you can look at if you exponentiate these guys, anyway here e to the x gives you the group element. Here e to the 1 gives you your 0, and then what we're using, the fact that we're for translation groups, we're using exponential coordinates. We're using the same coordinates on the Lie algebra and on the Lie group, and then we're taking the exponential map to just be the identity. So in our standard exponential coordinates, the exponential map doesn't change anything here. It makes this a 1, and it makes this this e to the x to r. So this is the kind of thing. This is the kind. You can think of it either way. Exponentiating these guys will give you these guys, or you can check that. You can also just do the computation and see how it works, or you can also say, well, what are the things that are infinitesimally close to the identity matrix to the identity here? Well, it's going to be the x's, which are infinitesimally close to the 0 here, and then a is here, except you should think of them as infinitesimal. Okay, but anyway, and now what you want to do is then take the okay. So now the Lie algebra is Lie algebra matrices of this form, and you can then compute what the Lie bracket is, because once you have a matrix Lie algebra, it's just the commutator of matrices. So it's because I wrote this out here. So if you take x1 a1 or 0 0, if you commute 2 of these guys, you find that what you get is you get the in this here you just get the x1. Let's just write it out. Yeah. So here you just get the Lie bracket in SOD. So as far as this kind of upper left hand d by d corner is concerned, you're really just doing SOD. And everywhere else you're going to get zeros, and here you're going to get zeros. But what's interesting is here is that you get 0. Is that you get something interesting happening to the a to the a's, which is this. You get x1 a2 minus x2 a1. And so this is just the computate, just compute what happens if you take multiply these matrices and take the difference.
Sorry, going back to, so this exponential map is not just like the normal exponentiating a matrix, right?
It is, yeah.
So if it is, then, so if I think of like the one-dimensional case,
yeah,
and if I exponentiate this Lie algebra elements,
yeah,
and wouldn't the upper right-hand element be like this E of A?
No,
A?
yeah. I mean, Yeah, I mean, you know, watch it. You can do this computation, and you'll see that what happens is yeah. So it's e to the I mean e to the 1. Yeah, what happens is this. Sorry, e to the. Actually, I mean, what really happens is this. So this is 1. Wait. Well, it's 1 plus 0. Okay. I mean, if you start, so the exponential is the identity plus, e to the x is 1 plus x plus higher order in x, right? But now, if you start multiplying this guy by itself, it's nilpotent. It's going to be 0. Okay. So this is actually equal to 1a 0 1. Okay. So yeah. So the way the exponential works, you see, you don't get actually. You don't get e to the a. You just get a. Okay. It's kind of tricky. It's kind of a little bit miraculous that it works this way. But there's something funny about kind of nilpotent matrices, about matrices that once you start multiplying them, they become 0. Then they don't behave quite like you would expect sometimes. Okay. Okay, and then anyway, so you can see what's happening is that the anyway, I could rewrite this formula in terms of pairs x and a, and then the Lie bracket of a pair x1a1 and a pair x1a2 is the pair Lie bracket of x1 x2, and then this this combination. But it's just, or I could just leave it in terms of matrices. It's the same calculation. But you can go back and forth between thinking of these guys as pairs just given by the first row, or you can think of them as matrices given this way. Okay. Anyway, then I guess I also then wrote down the I can write down the this is the main case you care about. And the same thing is going to happen. So the main case you care about is actually this, and also the same case for the Poincare group, where this is where this D becomes a D, comma 1, and then but it's exactly the same formulas work in those cases. So the same formula works in the Poincare case. Let me just write down the kind of abstract version of it. It's a general version. Is this, and this is what's called a semi-direct product. The algebra. And we'll write this. I guess I want to. So so we'll write this as Lie n again, and I'll use the same symbol Lie k. Actually, sometimes you'll see. What did I do here? And there's kind of an argument that the where do I want to do this? Okay. I mean, there's a somewhat of a moral argument that when you're at a group level and you take a product, you should think of it as it behaves multiplicatively. You should think of it as an x. But then when you're at a Lie algebra, since these things are going to get exponentiated group elements, they behave additively. so sometimes you'll see people try to come up with a weird symbol here that it's you know, a plus with some kind of, I don't know. Anyway, you have to. Anyways, so sometimes, arguably, this x here is not such a great idea that you should have a plus and then I don't know, something like this maybe. But that's kind of a matter of anyway. That gets too confusing, so we'll stick to this. But again, the symbol has the same problem that you really need to know how k is going to act infinitesimally on n. And then otherwise, you don't really know what this means. But if you do know it is, okay. Did I actually say this again? Okay, so here, so you could construct this. Just given, one a Lie algebra, and I'm writing it as a Lie algebra of a group, but it could actually be an arbitrary Lie algebra, which doesn't necessarily come from differentiating a group, but you've abstractly done, and then a Lie algebra. Okay. And then you need what's kind of you need what you mean by the infinitesimal action of this guy on this guy. So an action of elements y. Let's see. Okay. So what do I need? Elements y element of k on x element of the n by you need to know what this is. And so I'll write this by x goes to for notational reasons, I'll sometimes just write this as y dot x. Okay. And so this dot is what carries the infinitesimal version of what we were calling phi in the case of a group. But we just need an element here, and it turns so. And in the case of okay, so. I don't know that I've done this particular piece, but now I'm a little bit worried that I haven't done this piece of general theory that I need. Is that so what we had in the case of the semi-direct product Lie group was we had an action of k on n by automorphisms, and that meant that k acts. And I wrote it down. For each k, you have a map from n to itself, which takes n1 and phi of n1 n2 times n2 is phi of n1 times phi of n2. That was, but you need to know what's the kind of infinitesimal version of that same thing, and that's what's called a derivation. And let me. Maybe must be a derivation, and this is the analog of phi, and that must be an automorphism. Well, I forgot that if I write up the anyway, now I'm worried that I never told you guys what a derivation was. Let me leave this away for now and then, because if I start trying to give the definition of that off the top of my head, I may get it wrong. So let me but there's an analog. There's an algebraic condition of the analog of being the infinitesimal analog of being an automorphism. It's called being a derivation. It's kind of anyway, yeah, it's a derivation. And then I actually wrote down the Lie algebra. The Lie bracket is what it's that if you take pairs. Yeah. So again, like in the semi-direct product group, where you're taking pairs of elements in N and K, here you're taking pairs of elements in Lie N and Lie K, and you have to know what the Lie bracket is going to be, and the Lie bracket is what you'd expect. So as far as these guys are concerned, it's just x1, x2. But then, in general, something funny it happens to the instead of having the usual bracket of y1 and y2, you have to take into account the fact that y acts on x. Sorry, wait a minute, I got this backwards. Wait a minute. Huh. X, y. Yeah, sorry. There's actually. Okay, and I see what I did. So I've got one. Yeah, I wrote this wrong. So what's going to happen over here is it's going to have it's the y's that are in K, and they're going to do the usual thing. And then the funny thing that's going to happen is the fact that the y's act on the x's. So you actually get so you get a term where the x, you get the usual term with the x's, but then you also get a term that's where this comes into play, and it's y1 acting on x2 minus y2 acting on x1. Anyway, so this is the general story. And what happened in the case that we were looking at before in the so what happened in the case of the Euclidean group was that N was actually a commutative group. It was just the group of translations. It was just the commutative group RD. So if you look at this formula, it's actually the same formula we had for the Euclidean group, except in the case of the Euclidean group, this term didn't occur. This term was 0. This was just the rotations, and this was just the way the rotations act on the translations infinitesimally. Okay, but this in some senses perhaps too much general theory, but this is the most abstract thing there is to say about and so you can now go and anyway, so you can work out exactly what this says for the Jacobi group, and but for the Jacobi, but it's a little bit silly. This is kind of way too high powered for the Jacobi group, because in the Jacobi group we actually had our hands in the Lie algebra in a much more simple way. The Lie algebra was just the quadratic polynomials. So this is kind of a high power technology for any semi-direct product Lie algebra. For the Lie algebras that we care about, they're just the Euclidean one where things are simple because this action is simple and you don't have this, and they're the case of the Jacobi group where things are simple because it's really just the Poisson bracket of quadratic polynomials. So you don't need all this complicated theory. So I kind of wrote, I don't know, at some point I decided it would be a good idea to write down the general theory, but I'm not really arguing that you should spend a lot of time pondering this general theory, because the examples that we actually care about, it's have some simplifying features, and the simplifying feature either is that this is 0 and this is a simple action, a very simple to understand action, or that that the whole thing is kind of way overpowered because you're just talking about the Poisson bracket of quadratic polynomials. Okay, so let me see what else. Okay, so anyway, maybe it's getting close to a good end. Like this, so this is the end of kind of the abstract, way too abstract theory. So what we're going to do next is ask. Okay, oh, maybe there's one more thing to say about abstract theory. Just as kind of a general fact about mathematics that the so what happens if you're trying to classify Lie groups, if you're trying to classify groups, that's also true for finite groups. If you're trying to classify finite groups or Lie groups, the way you do it is you find the so-called simple ones. So you find ones that don't have any any non-trivial subgroups. You find the so-called simple ones, and then you realize that, well, I can take products of the simple ones and get so-called semi-simple ones. That's fairly easy. But the kind of horrible fact of the matter is that you can also not just take, as we've seen here, because one group can act non-trivially on another, you can take not just the product but the semi-direct product. So the whole classification problem for groups is kind of an impossible problem. It's impossibly complex, and it's hard to actually even write down some theorems saying what the most general Lie group or most general finite group is going to be, and it's all because of the complexity as your groups get bigger and bigger. The complexity of how one can act on the other by automorphisms just gets more and more complicated. So you end up with more and more possible semi-direct product groups, and you end up with a horrible story. But anyway, we're just going to see a couple very simple examples of it. So let me just then say a bit about what's next. Okay, so what are the representations of a semi-direct product? So this is the question. And again, there's a general theory. So what if somebody hands you two Lie groups and you know everything about the representations of one Lie group, everything about the representations of the other Lie group? What can you actually say about the representations of the semi-direct product? And it turns out that it's complicated in general. And even specifically for for the so-called Jacobi group that I wrote down, you can we've basically found one really interesting representation by taking this kind of unique representation of the Heisenberg group and extending it to a representation of the bigger group. So we found kind of one interesting representation. But if you try and ask what are all the representations of the Jacobi group, you quickly get into a very complicated and a difficult problem. And in general, yeah, and there is a lot you can say about this. There is an interesting general theory, and a lot of it's sometimes called Mackey theory for parts of it, and that's the complicated story. But the simple story, relatively simple. For n commutative. And so and for instance, nk is the Euclidean group or Poincare. So what we're going to do, and I'll say more about this next time, is we're going to go to a special case, which is not which doesn't include the Jacobian group, because for the Jacobi group, N is the Heisenberg group, so it's not commutative. But it does include the Euclidean group or the Poincare group. And in terms of the anyway, the fact that N is commutative, and it makes the problem, all of a sudden much easier. That you actually can get a full theory of what's going to happen. And so we're going to I'll talk about that theory next time, and especially or next time or the time after. But anyway, I'll talk about that theory soon, and especially in the context of the Euclidean group and the Poincare group. And again, and very specifically, we'll work through what happens exactly for like the Euclidean group in 2 dimensions and the Euclidean group in 3 dimensions. It's a nice but non-trivial story. It has a lot to do with the theory of a free particle, and it's also something that doesn't, even though it's kind of interesting enough, too hard to understand, it often doesn't get written down. So I wanted to write it down very carefully here, and we'll work a bit on that next time. Okay. So any questions about any of this or about anything right now? Or again, you're also, please come back in a little while. We can talk some more about this or anything else. Do you have any questions about any of this? Okay. Anyway, so then if not, I'll see you on see you on Thursday. And this, at least, I think actually what I did today does fairly correspond fairly closely to what's actually worked out in somewhat more detail in this chapter 18. So hopefully if you can follow that, there's a little bit more detail somewhere in there. Okay, bye now.
Thank you.
Thank you. Thank you. Bye.
Bye.